What if I told you that you could significantly improve the performance of a large language model without retraining the model itself? Curious. Sounds impossible? Well, that's exactly what prompt fine-tuning, also known as prompt tuning, makes possible. Excited. Welcome back to the Prompt Engineering Masterclass series. I'm Satish Sharma, and in today's session, we're diving into one of the most powerful and efficient techniques in modern AI. In this video, you'll learn what prompt fine-tuning actually is, the difference between hard prompts and soft prompts, prompt tuning versus model fine-tuning, how prompt embeddings are trained, and why companies prefer prompt tuning over traditional fine-tuning for many AI applications. Whether you're an AI engineer, prompt engineer, data scientist, machine learning enthusiast, or simply curious about generative AI, this lesson is for you. So, without wasting any time, rushed. Let's get started. Let's begin with a simple, real-world analogy. Imagine you visit your favorite restaurant every week. The first time you go there, you explain your preferences to the chef. You like less spice, extra cheese, and medium seasoning. Instead of repeating those instructions every time, the restaurant gives you a unique customer code. The next time you visit, you simply show the code. The chef immediately understands your preferences and prepares your meal exactly the way you like it. Notice something interesting. The chef hasn't changed. The kitchen hasn't changed. The recipe hasn't changed. Only the hidden instruction, the secret code, changes the final output. This is exactly how prompt fine-tuning works. Instead of modifying billions of parameters inside a large language model, we attach a small set of trainable tokens to the user's prompt. The model generates a response. That response is compared with the correct answer. A loss function measures the error, gradients are calculated, and only those hidden prompt tokens are updated. Gradually, these learned prompts become highly optimized, allowing the model to perform much better without ever changing the model itself. Now let's understand the terminology behind this process. Before we go any further, let's clarify some important terminology. Curious. One of the biggest misconceptions among beginners is that prompt tuning and model fine-tuning are the same thing. Pause. They're not. In prompt tuning, the large language model remains completely frozen. None of its internal parameters are updated. Instead, training focuses only on a small set of learnable prompt embeddings that are added before the user's prompt. These learned embeddings are called the soft prompt. On the other hand, the text that you type manually, such as summarize this article or translate this paragraph, is called the hard prompt. A simple way to remember this is thoughtful hard prompt equals written by the user. Soft prompt equals learned automatically during training. Because only a tiny number of parameters are optimized, prompt tuning is much faster and requires significantly fewer computational resources than traditional fine-tuning. Now let's compare prompt tuning with traditional model fine-tuning. Curious, suppose your company has 3 AI tasks: translation, text summarization, and sentiment analysis. With traditional fine-tuning, each task usually requires its own fine-tuned model. Size. That means maintaining multiple versions of the same language model. Training each one requires expensive GPUs, significant storage, and a lot of time. Prompt tuning takes a much smarter approach. Excited. Instead of creating multiple models, we keep a single pre-trained model. For every task, we simply learn a different soft prompt. One model, multiple prompts. Excellent performance. That's why prompt tuning has become one of the most popular parameter-efficient techniques in modern AI. Let's visualize the entire training process. On the left side, we have traditional fine-tuning. The input is sent into the pre-trained model. During training, millions or even billions of model parameters are updated. Exhales. As you can imagine, this is computationally expensive. It requires powerful hardware, large amounts of memory, and long training times. Size. Now look at the right side. In prompt tuning, the pre-trained model stays exactly the same. Its parameters remain frozen. Only the prompt embeddings are optimized during training. This dramatically reduces computational cost while still allowing the model to specialize for different tasks. In other words, less computation, less memory, lower cost, faster deployment. Excited. That's the biggest advantage of prompt tuning. Let's understand this with a practical example. Suppose we want an AI model to perform sentiment analysis. Curious shape. Our goal is simple. Given a movie review, the AI should classify it as either positive or negative. We already have a dataset containing thousands of labeled movie reviews. Instead of sending only the instruction, classify this review as positive or negative, we prepend a set of trainable prompt embeddings to the input. Thoughtful. Initially, these embeddings contain random values. The model predicts the sentiment. For example, it might assign a 70% probability to positive and 30% to negative. Those predictions are then compared with the actual label. The resulting error is used to improve the prompt embeddings. This process repeats until the learned prompt consistently guides the model toward accurate predictions. Now let's see how the learning actually happens. Curious. Once the model makes a prediction, we calculate something called the loss function. The loss measures how far the prediction is from the correct answer. A smaller loss indicates better predictions. A larger loss means the prompt still needs improvement. Thoughtful. Next comes gradient descent. Think of gradient descent as a navigation system. It tells us which direction the prompt embeddings should move in to reduce future errors. The learning rate determines how large each update should be. If it's too high, training becomes unstable. If it's too low, learning becomes extremely slow. Using these gradients, the prompt embeddings are updated repeatedly until they become highly optimized. And remember, pause. The language model itself remains completely unchanged throughout the entire process. Congratulations! You now understand the complete workflow behind prompt fine-tuning. Excited pipe? The resources shown on this slide include official implementation guides from Hugging Face and IBM. If you want to build production-ready prompt tuning applications, I highly recommend exploring these tutorials and experimenting with the code yourself. Hands-on practice is the fastest way to master prompt engineering and generative AI. Now that you've learned the theory, it's time to apply it in real-world projects. Encouraging. So that's a complete overview of prompt fine-tuning. Today we learned what prompt fine-tuning is, the difference between hard prompts and soft prompts, prompt tuning versus model fine-tuning, how prompt embeddings are trained, and how loss functions and gradient descent optimize prompts without changing the language model. If you found this video helpful, don't forget to like the video and share it with your friends, classmates, or colleagues who are learning AI. If you're new to the channel, make sure you subscribe and hit the bell icon so you never miss the next episode of this Prompt Engineering Masterclass. Enthusiastic. Also, let me know in the comments, have you ever experimented with prompt tuning, or is this your first introduction to it? I'd love to hear your thoughts and answer your questions. Thank you so much for watching. I'm Satish Sharma, and I'll see you in the next lesson. Until then, keep learning, keep building, and keep innovating with AI.